So as immediate follow-up to trigonometric integrals from 7.2, we have trig substitution. And this is section 7.3. And what this is it's a standard way of dealing with integrals which contain the sum or difference of squares. And really the best way to set this up is to just simply do one. So why don't we find out what the area of a circle is? So we're familiar with this equation of a circle, x squared plus y squared equals r squared. So if I have a circle of radius 1, I'll have this equation. And if I solve for y, I'll have y equals a positive or a negative version of 1 minus x squared under a square root. So what we can do to find the area of the total circle is we can find the area of half the circle, namely the top half. So the area of the circle is going to be equal to twice the integral from negative 1 to 1 of the square root of 1 minus x squared. But so far we haven't had any real good method of dealing with this kind of an integral. Even if I were to try to attempt this by parts, I would kind of get stuck pretty quick. Well, I probably wouldn't be stuck. I'd be able to keep going, but I'd have to do so many integration by parts that I would actually end up going nowhere. So the way that this works is this. I have a sum or difference of squares somewhere in my integral, namely right here, and I use that to try to build a triangle using the Pythagorean theorem. Since I have a 1 minus x squared and the 1 comes first, I'll assign the 1 to the hypotenuse and x to one of the legs. And then the third side, by the Pythagorean theorem, will be equal to the square root of 1 minus x squared. And I'll toss an angle theta onto one of these angles. It actually doesn't matter which in the grand scheme of things. So I have the following new equations. If I take sine of theta, that's opposite over hypotenuse, so sine of theta is equal to x over 1, which is just x. If I find cosine of theta, well, that's going to be equal to adjacent over hypotenuse. That's equal to the square root of 1 minus x squared. And I could actually fill out all of the trig functions using this triangle and this angle theta. But what I'm most interested in right now is that cosine of theta is equal to the function inside of my integral. But before I can do any substitutions, I first need to find out what the dx is going to be equal to. And I find that from my first equation up here. So I'll take the derivative there. The derivative of sine of theta is going to be cosine of theta d theta, and the x becomes dx. So when I substitute into my integral of 2 times, I won't have the same bounds anymore, so I'll just put a couple of question marks until I figure those out. But the square root of 1 minus x squared, that's equal to cosine of theta. And my dx is equal to cosine of theta d theta. Notice that if I were to try to attempt the bounds on this, I would have to solve one of these upper equations for theta. I could probably do that with the sine of theta, and so I'd be looking at theta equal to the arc sine, of x. So if x is equal to negative 1 and x is equal to positive 1, I'm going to end up with bounds from negative pi over 2 to positive pi over 2. and this is of cosine squared of theta d theta. And fortunately, we just had a whole section on dealing with these kinds of integrals, so I'm going to use the half angle identity. It's equal to 2 integral negative pi over 2 to pi over 2 of 1 plus cosine of 2 theta all over 2 d theta. So when I find this antiderivative, if you allow me to skip the u substitution for the second half of the integral, I'll have 2 times 1/2 x plus, nope, not x, theta, plus 1 over 4 times the sine of 2 theta. And this is evaluated from negative pi over 2 up to positive pi over 2. Which looks awesome, right? So let's see, I'll have theta plus 1/2 sine of 2 theta from negative pi over 2 to pi over 2. So when I evaluate, I have pi over 2 plus 1/2 of sine of 2 times pi over 2, which is 1/2 of sine of pi, which is 0, minus negative pi over 2 plus 1/2 sine of 2 times negative pi over 2, which is sine of negative pi, which is, again, 0, giving me pi. In fact, this fits what we know for the area of a circle. Area equals pi r squared. So a fun exercise would be to redo this example, but instead of having a 1 here, we have an r squared. And by the end of the integral, we'll have a formula describing the area of the circle in terms of r, and you'll find that the answer is going to be pi r squared. And this works for pretty much any sum or difference of squares you could come across. If I wanted to do 2x over 9x squared minus 4 dx, then I would again notice here, right here, I have a difference of squares. They don't have to be perfect squares because any real number has a square root. So I'll draw my triangle. The 9x squared comes first in the difference, so it's going to be the hypotenuse. But instead of having 9x squared, that's the square of the hypotenuse, so this is only going to be 3x, because 3x squared quantity is equal to 9x squared. I'll have 2 for one of the sides, leaving me with the square root of 9x squared minus 4 for the last leg. I'll pick an angle theta. So it looks like if I say that sine of theta, this is going to be equal to 2 over 3x. Or if I flip it, let's see, 1 over sine is cosecant. This will be equal to 3/2 times x. And this right here, the grouping of the two simplest sides of the triangle into one trig function, is the best way, or the simplest way, to do all of these problems. Because when I make the substitution into the original problem, all the nasty stuff is going to go away. So I'm going to need a derivative. The derivative of cosecant is cosecant theta times cotangent theta, and that's supposed to be negative d theta. And this is going to be equal to 3/2 dx, or dx is equal to negative 2/3 cosecant theta cotangent theta. So if I go back to my original problem, rewrite it a little bit, I had 2x all over, let me write it this way, 3x quantity squared minus 4 dx. My x here was equal to 2/3 cosecant of theta. And my dx is equal to negative 2/3 cosecant of theta cotangent of theta with a d theta. So I'm going to substitute all of these parts. 2 times x, which is 2/3 cosecant of theta, all over 3, parentheses 3 times 2/3 cosecant of theta. All of that is squared, so that's my x right there, minus 4. And the dx is negative 2/3 cosecant theta cotangent theta d theta, which looks totally awful, I know, but we can simplify this a little bit to give ourselves an easier problem. So in the top half of the fraction, I have 4/3 cosecant theta times, I'll just move that up there, another negative 2/3, another cosecant of theta, and a cotangent of theta. And on the bottom, 3 times 2/3, those cancel. And when I square all this out, I'm going to have 4 cosecant of theta squared. Or I'll say cosecant squared of theta minus 4. And there's a d theta waiting patiently out here. But if I were to factor out the 4 from the denominator, I've got negative 8/3 on top, cosecant squared of theta, cotangent of theta, and on the bottom I'll have 4 cosecant squared of theta minus 1. And sure, we can cancel this 4 and this 8 to leave ourselves with a 2, but what's most important is this cosecant squared of theta minus 1, that's equal to cotangent of theta. That's one of our Pythagorean identities. 1 plus cotangent squared of theta is equal to cosecant squared of theta, or cosecant squared of theta minus 1 will be equal to cotangent squared of theta. So this replaces with cotangent squared of theta in the denominator, which lets me cancel one of these with one of these. And it just so happens that cosecant squared is the derivative of cotangent. More specifically, the derivative of cotangent is negative cosecant squared. So I'm going to factor out the 2/3 all the way outside of the integral. I have negative cosecant squared of theta all over cotangent of theta d theta, and now I have myself a u substitution. Which means my du is equal to negative cosecant squared of theta landing me all the way down here, oh boy, with the integral of 1 over u du, leaving me with 2/3 natural log absolute value of u plus c. Now I got to undo all of my substitutions. I've got 2/3 natural log u was equal to cotangent of theta. But to find out what cotangent of theta is equal to, I got to go all the way back up to my triangle that I made for this problem. That's a lot of work. Cotangent of theta is equal to adjacent over opposite. So cotangent is going to be the square root of 9x squared minus 4 all over 2. All the way back down. So it's equal to 2/3 natural log square root of 9x squared minus 4 all over 2 plus c. Now the book has some guidelines. If we see x squared minus a squared, then we're typically going to use secant of theta equal to x over a. Now, I had one of those right up above there, but I used cosecant. And the difference between using cosecant or secant is basically just which of the two angles on your right triangle that you choose to label. It's essentially the same process the whole way through. If you have x squared plus a squared, then you're going to use tangent of theta equals x over a, opposite over adjacent, or, depending again where you label your angle on your triangle, you're going to have cotangent of theta equal to x over a. And lastly, if I have a squared minus x squared, then I'm going to use sine. Or, again, for the third time, depending on where you label your angle theta on your triangle, you'll be using cosine. Now, the guidelines are there to kind of help things move along, but really, you should be drawing the triangle as your first step for every single one of these, because you're going to need the triangle at some point in the problem. So let's suppose I had another problem, which looked like the integral of 1 over x cubed minus plus 2x. There's dx on here. I don't actually have a sum or difference of squares here at first glance, but if I rearrange what I have here, I'll have 1 over x times x squared plus 2. And now it fits something from this section. We're actually going to have another way to do this problem in the future in the very next section. So what I'm using here is I'm using this x squared plus 2 as a sum of squares. According to the chart I had above, that means I'm going to be using either a tangent or a cotangent. But I always draw the triangle. I'll just put an angle theta here. Now since I have a sum here, that means that's the hypotenuse, x squared plus 2. So, as the legs of my triangle, I'm going to have an x, and I'm going to have the square root of 2. So let's see here. The tangent of theta in this triangle is going to be equal to x divided by the square root of 2, which looks like it's already a very good choice. If I had chosen to use my angle at the top of the triangle, then I would be using the cotangent right now. So, learning from the last one, I'm going to move this 2 over first, equals x, and now I'm going to change, or not change, but I'm going to find out what the dx is going to be equal to. So the square root of 2, the derivative of tangent is secant squared, so root 2 times secant squared of theta d theta equals dx. And that's my substitution stuff. So when I do that, thankfully I don't have bounds. I go from, no, I just said I don't have bounds. I have 1 over x is equal to square root of 2 times tangent, root 2 tangent theta. And again, x is equal to root 2 times tangent theta, or if I jump ahead, the square root of 2 times tangent theta all squared is going to be 2 tangent squared of theta plus 2. And my dx is the square root of 2 times secant squared of theta d theta. never forget to find your dx in terms of d theta. It's a very important step, and it's something that I often forget to do. Now these root 2's will cancel, and I can factor out this 2 down here in the denominator. So I'm going to do that. I'm going to have secant squared of theta on top. And I have 2 tangent theta, tangent squared of theta, plus 1. We'll see here, this is another one of those identities, d theta. You might notice that I have tangents on the bottom and secants on the top. And I could say, hey, I could let u be equal to tangent of theta. And I could do u substitution. But guess what? That would take us all the way back to the original problem, which is not helpful. So what we should do is we'll use the identity to simplify this guy. Secant squared of theta here, and 2 tangent of theta here, and this turns into secant squared of theta by identity, d theta, and so these cancel. So in the end, I have the integral of 1/2 times cotangent of theta. And if you recall this one, this is a simple u substitution problem, but if I recall, and I do recall, this is going to end up being 1/2 times the natural log of the sine of theta plus c. Now when I go back to x's, I need my triangle again. I don't know what the sine of theta is. I haven't found it yet, so I'll go here. Opposite over hypotenuse is sine, so I'll have x over x squared plus 2. And that's what it is to do trig substitution. So let me move back up to my chart here. Some identities which are going to come in handy for all of this. Sine squared of theta plus cosine squared of theta, we should all know is equal to 1. Now if I divide both sides of this equation by sine squared, I'm going to get 1 plus cotangent squared of theta equals cosecant squared. And if I were to take the original and divide both sides by cosine squared, I would get tangent squared of theta plus 1 equals secant squared. So as a first exercise, try to do all 3 of these problems that I've done by choosing the opposite angle in the triangle and comparing it to what I got. In some cases, you get a slightly different answer, or a slightly different looking answer, which is actually equal to, or is, what's the word I'm looking for? Difference of a constant with what I got.